instrumentation that tells you temperature is a function of altitude, temperature where they are, and maybe humidity, I'm not actually sure. That information gets fed into all these models. So the fact that we have airplanes flying everywhere is actually kind of important. A lot of the visualization data comes from satellite imagery, so they're going to look at the ground and say, look, there's snow there. Turns out the snow matters a lot because when the sun shines on it, it reflects. And it also melts and makes silhouette and all sorts of things. And also the satellites tell us about where clouds are, things like that. They also send up balloons to measure pressure as a function of altitude. All these things go into these models. It would be neat if all that data was available in an easy way. But it turns out that generating visualizations of weather like this is hard in a general sense. First of all, because what a weather person might be interested in is not necessarily what we're interested in. So you have to get a weather person who really wants to communicate weather beyond all the details that they're concerned about. Anyway, that was a bit of an aside. So this is Saturday in Pemberton. So I woke up and I looked at this, and so what did I see? So first of all, I saw that the wind was light. So for example, down and around launch height, lower launch, because we can't drive to upper yet, the wind doesn't even have barbs on it, which means anywhere from 0 to 5 kilometers an hour. That's great, at least for us paragliders, because we don't go very fast, and that means low wind-induced turbulence. It means you can go cross-country without getting blown over some mountain somewhere. So that was the first thing I saw. Even up at altitude, so at way high altitude, of course, the winds are always high. So don't look up at way above where you're going to get to. In this case, it said that there were going to be puffy clouds. That's what these white things are. Even clouds, not marshmallows. It's again built into this. This is the thing that generates this is actually a language sort of developed toward visualizing weather stuff. So it has clouds and moons. The moon is not. It's rotated, so it looks like a paradox. So what it was saying is that at 8 in the morning you could be at 1,000 meters. We know that is not the case. You cannot go up to Pemberton and launch at 8 in the morning and be at 1,000 meters. But so you have to do a little bit of fly the site, compare to this, and go back and forth. But what it says is the paragliders were in the clouds from 10 a.m. until around 1 p.m. Now we know there wasn't complete cloud coverage in Pemberton. So I was out there. There were little tiny sort of wispy, not really fully developed clouds. Especially in the afternoon, they kind of disappeared. So this is saying there was cloud in the morning. Probably some leftover moisture on the ground, I don't really know. And the paragliders never go above the clouds. So that's one thing to know. If you see clouds, the paragliders are always going to be at them because it's illegal to go above them, so we don't visualize the paragliders above them, even if you could from past them.
Those ones are clearly inside the clouds.
It's all about perspective.
Just the wing.
Yeah, that's right. Yeah.
Just the wings. Okay.
Pilot's running.
So using this background color scheme, so let's go through that, for example. So here it says that when I go up from launch height up to around, this is somewhere, let's say 1,700 meters, the color starts to get less than 2 degrees per 1,000 feet. You can see there are labels here. So when it gets to be stable air, that means really nothing is going to rise past that. Anything up here, between say minus 1.5 and 2.5, if there's hotter air below it, chances are the air will continue to rise through it. So up here we know that the thermals, so early in the morning, this is 8 a.m. to about 1 p.m. What it's showing is that the paragliders and the thermals would get up to maybe 1,500 meters and they would just stop. Okay. There were also clouds there because there's this uncharted section of air left over from the morning, from the night. And eventually by about, so somehow there's a bug in here and these like nighttime numbers are showing up there. You just have to ignore all the bugs and just look at the good stuff. So ignore the 6 and the 7 that should be living here. I've never noticed that before. But by about 1 p.m., top of lift was predicted to be about 1,800 meters. 2 p.m., about 2,000. And by 4 p.m., maybe 2,200. And then at 5 p.m. it all shuts down and the paraglider gets low. Even though from the background colors you wouldn't really expect that. So what actually happened was that we launched around 1 p.m., which is the typical launching time in Pemberton. Unless you get to upper launch and it's an epic day. We're typically launching around 1 p.m. We pretty much pinned out to 2,600 meters right then, maybe 2,400. So obviously the predictions were a little bit off because we were up around here. And it's a little hard to predict. This air here is this conditional, a little bit less than 2 degrees per 1,000 feet, but there was a lot of heating from down below. So what we do to calculate these paragliders, we take a parcel of air on the ground, and we just raise it up and cool it down, raise it up and cool it down until it eventually hits this temperature. If you increase the ground temperature by, say, 1 degree, this might be off the scale for all we know. So I don't show you how uncertain this prediction is. So you just have to get a feel for it. And that's what that background color tells you. So chances are you're not going to really get up to 3,000 meters on this day because this is not even conditionally unstable, but maybe you can get a little higher than that. The other thing to notice on this are these sort of black lines. These are actually telling you the temperature at that altitude. That's what these numbers are calculated off of. So for example, at 4:30 p.m. at 3,200 feet, it was going to be about 8 degrees. This is really useful if you're deciding what clothes to wear. You go look at the paraglider, and up here, the paraglider is at minus 2 degrees. Minus 2 degrees and 40 kilometers an hour of wind. It's going to be really, really cold. So bring more clothes on that sort of day. So that's why we have the temperature things here. It's kind of important, because you don't necessarily know. This windgram starts at 509 meters. It's not exactly at Mackenzie launch, so the other thing to know is that this weather prediction, what it does, it takes the world, which is a very detailed thing with millions of people and lots of terrain, and it breaks it up into 2.5 kilometer grid chunks. So it takes basically all of Pemberton, maybe a half a kilometer on each side, and it just treats that as one point in the line. Which means that the mountains that are really sharp and spiky get sort of averaged out. So in fact, it turns out that this windgram point, if you were to look at the windgram selector, lives actually out in the valley. So it's typically more pessimistic than the actual what would happen if you were on the edge of the mountain. It turns out that that's why I think that using a single point on the windgram is not the way to go. Because it may be that the top of lift is actually a lot better if you look over the mountains. So
Sorry to interrupt. Is that peculiar to Mackenzie that it's out in the valley, or is that kind of an average for everywhere?
It turns out we put Mackenzie in the valley because I wanted to capture, or closer to the valley, because I wanted to capture the Whistler Express winds. And you can see that it's up on the mountain.
So it could be marginally different at any given location.
Yeah, it won't change that much, but the top of lift where the paraglider goes to might. So the way to see that is if you can go back to over here, if you just go to CanadaRASP.com without /windgrams, you end up, the actual landing page you get is this. And so this is the main interface, though it's actually not what people use. So, yeah, you have to go here if you want to zoom out. But this is a map of the area. You can, it's a little bit complicated to interpret, but there's a title for what it's plotting. This is showing, for example, wind at 120 meters above the surface. The scale here.
I'm going to go to Pemberton.
Okay, yeah.
Wow.
And find, you have to go to the model, you have to go to HRTPS BC archives. If you want to go into the past, when you start this thing up, it only goes about, until the forecast under model. Yeah, so if you go to HRTPS BC archive, this has historical data. I put up this archive because there was a company that they like looking at windstorms and how much it causes waves on lakes that then destroy people's property. They're good people, they actually repair things, but they needed to know these things, so they wanted an archive, so I added this. So if you want to look in the past, you go to the BC archive. So that was April 20th at 10 in the morning. This is Pemberton. Sorry? Let's go to, if you scroll all the way down, so these are the type of things you can visualize. So wind at various heights, keep on going. Top of lift above ground level, for example. So this shows where that paraglider would be at every point in the graph. So when we go to maybe 1 p.m.
Yes. So those are the 2.5 kilometer parcels.
Yeah, so these chunks, they actually don't represent the real underlying model because the underlying model is on a very weird grid. Here I've kind of rotated them and resampled them, but it doesn't really matter. So let me talk through some of these details. So if you close this thing, you hit that X thing, it makes it look cooler. There's also another menu here that has the donate button, I think. And then we are funded half of the cost of the RASP probably by WCSC.
Yes, indeed.
Anyway, to get from here to the wing ramps, is when that thing comes up, there's a wing ramp like at the top of it. So it's just, because most people use the wing ramps, you would just click on that to get there. But if you go back there, sorry, remote controlling you click on show wing ram locations. This again looks like the other map. So Mackenzie is actually sitting here. Now the underlying terrain, there is actually something here that says terrain is currently broken, so don't click on it. It just doesn't work. I don't know what I did. I broke it. But it's out in the middle of the valley. We know that the terrain is going to be averaged out by this 2.5 kilometer thing, but roughly it's going to be in the valley. So let's scroll out a bit. At this time of year, so what do we expect up in the mountains? We know there's a lot of snow. And so even at 1 p.m., what this is showing, so on this this sort of color scale here, it says this is top of lift above ground level in meters above ground level. So we're seeing in the valley it's showing, it's a little hard to do the colors. Sometimes if you change the opacity, you can get them to match well. I'll sort of leave that to you guys. It's saying that you're going to get about between 1,200 and 1,600 meters above ground level. So why isn't it showing that up on the mountains? And it's usually at this time of year, it's because they know there's a lot of snow up there. And usually, if you have, okay, so snow is white, sun reflects off of it. So it means that you don't get a lot of heating on there. So unless you have a huge area of snow, you're not typically going to get lift off of it. Typically where you get the lift is, of course, where the snow line meets the non-snow line. So sometimes you can fly along there and get just an incredible, just not even turn, because all the warm air from the valley and from the side of the mountains hits the snow line with cold. Typically there's a little cold air coming down, releases there. So that's actually why most of this, even up in the mountains, you're seeing less lift than sort of near the valley edge. That's specific to this time of year when there's a lot of snow in the mountains.
That's lift above ground level.
Yeah, so the lift above, so there's also the fact that the mountains are higher, right? So you may see this anyway, but usually in the middle of the summer, the valley looks like a sinkhole because the air rises in the mountains and it goes down in the valley. Admittedly, this valley is not so wide that that's the case, but typically you cannot fly down the center of the Pemberton Valley and get lift. I don't recommend trying it unless you can try. There's some valleys when it's big enough that you don't see the mountains on the side, you can fly down the valley. But usually if there's a valley, it's all the air is moving up the side of the mountains and coming down. So that's why this is particular this time of year with all the snow on the sides. The other parameter we have here is thermal updraft velocity. So this is a very conservative average estimate of a conservative estimate of what the average thermal velocity is. So here it was predicting 2.5 to 3.1 meters per second. We had several climbs of 6 meters a second. The average climb was probably around 1.5 to 2.5 during that day, which is about what it showed. But we never take the average climb. Right?
Did you figure out that conversion? I was going to ask about that lift to lapse rate. How's that converted?
So this uses a model of thermals based on some studies by NASA. So yeah, but basically it is that. It's that you sort of say how much energy is being deposited into this chunk of air, what is the lapse rate. But it's a little bit more complicated than that because the actual, as you all know, when you're climbing in a thermal, sometimes the size of the thermal changes with altitude, for example. Sort of depends on how big the average thermal is. For example, if there was only ever one thermal right where the spot was, there'd be a lot of air moving through there. It would have to be pulling a lot of the heat from the whole surrounding areas. But we sort of know that the average thermal is about spaced by the distance to the top of lift. So there's all these sort of things that go into it. This is a really rough, pretty much bogus calculation. So when you look at it, don't look at it and be like, oh, it's only a 1 meter per second day, I don't want to go out. Don't use this as a quantitative measure. What you can use it for is when if you zoom out on this thing and you see that the entire interior PC is just going off, it's a day you want to go out there.
It's not the first time.
And it always looks like that. It's always better in the interior. It's drier. Even at this time of year, I don't know. The coast is wet. Anyway, so yeah. So like, what other things here? There are a bunch of other things. The wind at various altitudes. So sometimes it's worth doing that. Or well, okay, cloud cover. That's a good one. Let's choose that for example.
The colours are much better here too.
So, okay, this is a pretty good example. You can just change the time and scroll through. You don't have to do that. But basically it was showing there's a big bunch of clouds sort of north of Vancouver. And then it kind of, not much else up here. There's maybe some cloud in the big mountains. The best thing to do is not interpret the actual location, except when it's sort of around Vancouver, because we know that all this sort of marine air gets sucked into this valley here. But when you see things here, it's sort of saying, look, in the big mountains you might have some clouds. Maybe you scroll up to Pemberton and look a little bit earlier. I actually don't remember if they're going to be. Yeah, maybe like 12 or over. Are we on the same day? This is the 20th. Okay, well, it's not really showing any clouds, but it should be. Because on the windgram it showed clouds. I don't know, maybe this one was updated at a different time. But usually what you'll see is, for example, on a day with reasonable clouds, you'll see clouds over the mountain, but not over the valley, which is, of course, what you expect. The actual locations of the clouds are a little bit ill-defined. Just because you saw one over your local flying site really doesn't mean it's going to be cloudy on your flying site. It just means there's a chance of cloud or whatever it is. Sometimes you'll see cloud just in the big mountains, away from the valleys. That's a useful thing to know. Yeah, it just means that there is a chance of cloud other places. Okay, so that's sort of it for the maps. There are a bunch of other parameters.
Sorry, do you find the HRDPS model is most accurate for this area, or why did you choose that model versus some of the other options?
Okay, so the HRDPS is the highest resolution model that covers this area of Canada. So you need high resolution because, for example, the Pemberton Valley is not that wide. If you use the 15-kilometer model like the GDPS or the GFS or any of the other ones you might find around here, it doesn't even resolve the Pemberton Valley. It's not going to resolve the Whistler Express that comes up through Squamish and then into Pemberton. It's going to give you an average for mountains because there's no terrain really built into it. It's basically going to say it's the coast mountain. It's this big flat plateau of stuff. With a little bit of, it does have internally, it keeps track of the roughness to handle the winds. But, so yeah, you need to do flying prediction, you need high resolution. You need to be able to resolve valleys, side of mountains, things like that. 2.5 kilometers is not good enough, but it's sort of what you can do given computer math. You'll find that a lot of people run, so okay, this is called Canada RASP. The RASP part stands for Regional Atmospheric Soaring Predictor, which historically has meant people who took the data from, for example, the National Weather Services and processed it through a second set of calculations that predicts a much finer grid. So, for example, TJ's website, which I actually don't remember what it's called. Yeah. So that one actually runs a computer model on a BPPC based on the NAM model. It subsamples it to higher resolution and runs a separate model to try and correct it for the local values and mountains and things like that. It turned out that model was run at like a couple kilometers, so it really doesn't improve it much. Back before we had the HRDPS, the best thing you could get in Canada was like 15-kilometer grid, so you had to run that. So that's what we ran in the original version of the site. But it turns out that if you're a meteorologist and you have huge supercomputers, you can do a lot better than some guy with his PC in his house. So we stopped doing that because it was over-predicting winds and Pemberton and a big mess like that. So 2.5 kilometers, it just turns out that they tuned it well and it predicts well for our region. So we have a lot of experience using it. It's not bad. It's not going to be perfect. You need to learn about the sites that you're flying at to see how it correlates. But yeah, you need to have some resolution. And so the models we have that have that, the North American model, is about 2 kilometers. The HRDPS is 2.5 kilometers. And that's basically all you can get from high resolution. So we do have another model here. If you go to model GDPS, for example, this is the Canadian global model, and if you choose something that, top of lift, for example, you see the side that you zoom out. You can't even see the squares. The sides of the squares are like 10 kilometers on the side. It's not going to capture anything local about your site. So it's here because it predicts out 99, well, it predicts more than 99 hours. We download 99 hours of it. So basically it just sort of, you can see the chunks. They're really big. They're not going to tell you anything local. We have this so that you can do wind grams out for several days. Right now it didn't update this morning because there was an issue, but it also gives you sort of, if you're traveling to Mexico or something like that, there really isn't any other model to look at. If you're used to Canada RASP, you can use it. It'll have maps for, this covers the entire globe. You can zoom out all the way if you want. So anywhere you want, it'll show you what the top of lift is. Yeah, it'd probably be better to be down at the, Mexico. It's almost always better. If you go to HRDPS again, you can see that it covers all of Canada. You might just want to click down. You can do the normal HRDPS.
So is it safe to assume then that
we have to scroll up a little to see it.
the GDPS would be better for like predicting like meteo wind, and HRDPS would be smaller scale, or is there?
Well, so meteo wind. So it depends what you mean by that. If you mean the average wind over a huge area, yeah, it's not gonna be better because the GDPS feeds the HRDPS.
Okay.
You can think of the HRDPS as a corrected version of that. So when it actually starts with the GDPS model, it runs that forward some amount of time, then it uses that data to initialize the HRDPS and it corrects it.
So stick with the default.
Yeah. Okay. So this is actually where this is when the supercomputer runs. It runs this weird slice of the world. Mainly because they can't model the whole world because the world's big. So
Takes too much to do.
yeah. So I don't know. I'll probably open it up for questions. I think I've shown most of the things. I've probably left some things out. So ask me about the weather, or if you don't want to talk about weather, paragliding, XC paragliding competitions, safety, physics.
I don't know if you said this at the beginning, but it's new data that's calculated at 6 a.m. to 6 p.m. and then 12 o'clock and midnight. Those are just extensions of, like if you have bad data at 6 in the morning, is it actually progressively worse at noon? It's running the same.
Well, so I'll say something in general about that. In general, if the model has been off for about if it's been off, like really off, like it said it was going to rain and it didn't rain, chances are it'll be wrong tomorrow as well. It takes a while. There's feedback from the model's observation, but it's not like a switch. So if it gets way out, it's typically going to be, it's going to take it a day or so to recover. It's because you can't just say match exactly the observational data because we don't have enough observational data. If you did that, you'd just be introducing noise to the system. So what it does is actually, it nudges the model toward the observation.
Right, but the observational data is only collected for the 6 a.m. and 6 p.m.
No, it's updated. Well, okay. I actually don't know the data ingestion cycle for the GPS. They may only update it twice a day, but I don't know which it is. I would say the newest forecast is always better. I don't know how often the satellites re-image things, so yeah, I can't answer that. If you go to there's a link to
The donate button.
HRDPS, the donate button. There's the HRDPS model from WCSC. It'll tell you a little, if you go into here and start their models, they may tell you a little bit about, there's a lot of stuff on this website.
Oh my god.
And, so they'll tell you a little bit about it. They're usually pretty cryptic, but yeah, I don't actually remember when they ingest it.
Also, why don't you just send us emails of where you're flying and when and save me all this trouble?
Because usually I wake up in the morning and I'm groggy and I don't know where I'm flying until I have a coffee.
Which color gets you most whipped up?
Orange? So in general, red is great, except if red and orange proceed too high, that's usually a signal there to be thunderstorms in danger.
Oh, okay.
So you don't want the
That
upper
makes
air to
sense.
be unstable.
There's
another thing not on here, but if you go
That's a
to
good
maps,
tip.
there's something called CAPE. That's convective available potential energy. When that thing shows significant numbers, I won't go into what the numbers actually mean. It can be used to predict thunderstorms. If you're interested, you can read about it online. But it is there because...
Down, down, down.
Yeah, Cape, for example. Yeah, just a little rain. So typically when we're flying Golden in the middle of the summer or the end of the summer, we look at this a lot because typically we fly Golden when there's thunderstorms somewhere because it's mountains.
Cloudy and potentially exciting.
Check
That's what Kate heard.
So these sort of low numbers, below, you know, check yesterday a few hundreds joules per kilogram, it doesn't really matter. These don't mean anything, but yeah, you'll see on days. Like if you look at the standard weather forecast which says chance of thunderstorms, take a look here and see what color it is, and that'll give you some. I can't go back for it.
Use Cape.
Well, if you go to the archive, that's the thing. This the normal thing doesn't have the access to the archive.
Was yesterday a thunderstorm?
Does the Cape relate to the
Yesterday, I don't think so. But tomorrow
orange
maybe.
and red colors?
Well,
Yesterday we flew in Pemberton. It was
yeah,
pretty nice.
it's
Pretty stable actually. It was like a lot of cirrus.
Would it also?
Oh yeah,
To have,
yeah, it was
to
like
have some lift, you want some Cape?
Well, no. So Cape actually has to do. It's driven partly by the. So why do we get thunderstorms closer to normal rain? Normal rain comes from, you know, we get some warm air from the ground with some moisture running up, condensing and raining. When that water condenses, it releases more energy, which so just like if you try and boil water, you have to put heat into it. When it condenses, it releases heat. So that means that when clouds start to form, they start generating their own heat. That means that the air inside of them and the moisture inside of them rises more. And that's why you get cloud suck, for example. Is that the cloud, you can have a cloud with no air coming from the ground and still get sucked into it because it's heating up the air itself. And if that gets to be too strong, if the upper atmosphere is also unstable, then that warm air can then continue to rise farther and farther and farther until instead of just moisture, instead of just water and gas, you can start getting ice and all sorts of craziness, and then you get a thunderstorm and you die. So,
Nice summary.
Or they make a movie about it.
so typically on a day like that, you would see some, so these color scales are meant to be helpful. Red on the
Potentially
Cape thing
explosive.
means do not fly.
Blood. There's going to be blood.
Yeah.
Potentially explosive.
But these are the reason why I haven't tried to turn them into something that says, you know, thunderstorms here is because weather prediction is a bit of a crapshoot. So I just want part of this is to show here's what we expect, but it's still a bit sketchy. So you gotta.
Is that
The Cape is
joules
more
per
to do with
kilogram?
thunderstorm prediction?
Sorry?
The Cape is more to do with thunderstorm.
Yeah, that's for thunderstorm prediction. That isn't just the average of cloudy.
What about helicity?
Helicity, I don't visualize it here. That is typically another way to do.
Is it related to the thunder thing?
Yeah, that's, I don't actually remember what it is. I imagine it's actually, yeah, I don't remember exactly what I calculated, but that would be a very good predictor for thunderstorm.
Okay, so they're related.
Yeah.
What about what about high altitude cloud prediction? For example, we were flying in Pemberton yesterday.
And there was,
It seemed like a lovely day, but there was a lot of high cirrus, and it really tapped the day off. So we were basically scratching.
So I don't know if it showed up in here.
Yeah.
Sometimes you'll see it on.
Yeah. So sometimes when you look at the cloud cover and you zoom out, if you see features that aren't like cumulus clouds above,
It was Pemberton yesterday.
Why don't we look at yesterday, Pemberton?
Yeah.
yeah. So if you go to the,
Ooh. It's windy up high.
go to one day and go to yesterday. So I don't know what day it is.
I think 25th.
Nuclear.